Good afternoon. Today we're going to be taking notes for Unit 10, Day 1, Graphing Exponential Functions. And if I could tell you the two most important aspects of graphing exponential functions, it would, number one, be that you are aware of, in general, which way the curve should be headed. And number two, some of the algebra that you need to be able to calculate points for your exponential graph. So graphing exponential functions. All right, we're going to start with basic direction. And the generic formula we're going to use for basic direction is y equals some number b to the power of cx. Now, when we're talking about exponential functions, the larger number, in this case the b, is called the base of the exponent, and then cx is called the power. So we have a base and we have a power. And there's different ways that your curve will look depending on what b and c are. So go ahead and draw yourself a medium-sized set of axes. Okay, and we're going to start out with, let's say that c is some positive number, or it's greater than 1. If c is greater than 1, so some positive number greater than 1, your curve is going to be infinitely close to the x-axis, and then it will slowly get steeper, steeper, steeper without actually ever going vertical. Now, you know that any number to the power of 0 equals 1. So if x is 0, because of how this is put together, y is going to be equal to b to the power of 0x, which is b to the 0, which is 1. So one of the key points that we have is the point 0, 1, and that would be right here. And that has to do with the property of 0. Now, because of how this is built, there's no way in heck y can be a negative number if c is greater than 1. So what you have is an asymptote that is horizontal. And the asymptote is right at y equals 0. So unless you translate this graph up or down, that asymptote doesn't move regardless of what the other numbers are. What if c is not greater than 1? If c is not greater than 1, such as c is some number less than 1, then your curve will still cross at 0, 1, but it will come from the other direction. So infinitely close to the asymptote, crossing at 0, 1, and then accelerating more and more and more as it goes up. Now, those are both examples where c is changing value from positive to negative. Of course, if you apply a negative to the b on the outside, that's a reflection across the x-axis. So your rules of transformation still work. So rules of transformation still work. You can use the exact same ones that you've memorized for other types of functions. In general, if you're going to be graphing an exponential function, you need to have a minimum of 3 points to work with. Naturally, you want them to be whole numbers as often as possible, but that isn't always possible. Now, we're going to be working with a couple of logarithms in this section, and the first one we're going to start with is the natural log. So that's a certain type of base. So let's go to Roman numeral 2, and we're going to graph with a natural log base. So what does that look like? Well, your basic equation with the natural log base is going to be f of x equals e to the x. Now, lowercase e is a reserved letter. It's a little bit like the italicized I for imaginary numbers. E can only be used for one thing, and it's called the natural log because the ratio that creates E occurs in nature all over the place so often that they started to call it the natural log because it takes place in nature. For the sake of graphing, if you don't have a calculator, there's a few values of E that come in really handy. E to the power of 1 by itself can be rounded to 2.7. Of course, anything to the power of 0 equals 1. That's your hole-in-one winner. And e to the negative 1 is about 0.4. When it comes to graphing with e values or natural log values, it is acceptable to use these three values, including the decimals, because there just are not a lot of whole numbers with the value of e. Okay, so let's draw a pair of axes, and I'm going to move it over a little bit to the right. So if we plot our base graph, e to the x, of course you're going to want some way to organize, whether it's a t-chart or an h-chart or something. And again, these three values are really, really good for e. So if x is 0, 1, negative 1. Those are the three you're going to look at, and that's a positive one. So e to the 0 is 1, e to the 1 is 2.7, e to the negative 1 is 0.4. So if I graph those, of course, 0, 1, there is our number that rarely changes. Then I have a 1 and a 2.7, and a negative 1 and a 0.4. And remember that when you're graphing exponential functions, if the power is positive, you automatically have an asymptote at y equals 0. So it will get infinitely close, but it will not cross. So your graph comes up looking pretty flat, actually, and then it slowly gets steeper without ever going vertical. There's your base graph. So this asymptote, if you were to translate right or left, this would stay the same because your x values would just be sliding right or left. So horizontal translations are not an issue. Vertical translations, however, can create a change in this asymptote. So we're going to graph on this same grid another example. Y equals e to the x minus 2. And so looking at this, if you had to describe what the transformation is, this is a vertical translation down 2. So all of your y values are going to be decreased by 2. So if I make a new t-chart, basing it off of the old one, so 0, 1, and negative 1, 1, because you're subtracting 2. 1 minus 2 is negative 1. 2.7 minus 2 is 0.7. And 0.4 minus 2 is negative 1.6. When you're translating up and down, because these are decimals, counting spaces is not usually the best way to go because you have to have the labels on it anyway. Okay, so here we go. 0, negative 1 is here. Then we have 1 and 0.7, and then negative 1 and negative 1.6. And you can see why it's important to know where that asymptote is, because with just those 3 points, you really can't get a good shape. And again, this is your head knowledge. Your head knowledge is when you do a vertical translation up or down, that your asymptote moves up and down with the figure. So it used to be at y equals 0. Now that asymptote has dropped down by 2, and it is at y equals -2. You have to draw the asymptote in when you graph these. It's part of the critical structures. So there's your curve, infinitely close. And as the curve gets farther to the right, it's going to get closer and closer and closer. It will always be slightly bigger than the base graph, but they do near each other as they get closer to vertical. That's because the rate of change gets so small that they're almost indistinguishable. All right, last graph we're going to put on this one. So we'll call this one example 2. We're going to do y equals 7 to the power of x. So we're going to change the base on this to a 7. It's no longer natural log. So let me draw a t-chart. And again, 0, 1, and -1 still make really good values for x's because they're easy to calculate. So 7 to the power of 0 is 1, like all things. 7 to the power of 1 is 7. 7 to the power of -1 is 1 over 7. Remember that a negative power flips the base to the bottom of the fraction. The fraction isn't negative. The negative power just means the base moves. All right, let's plot this. So 0, 1 has not changed. Okay, so before we plot this though, base 7 compared to base E is 2.7. So 7 is quite a bit larger. So in this case, we are actually stretching the graph. We're actually doing a vertical stretch, but the rules for stretching by what ratio are different. We do know, however, that because this is a higher base, the curve should be steeper. And some might even say it looks almost more like a corner than a curve because it's going up so fast. So the 0.01 is still there. That hasn't moved. But what's going to happen is because this is a higher base, the curve's going to come up under the E, bend the corner like that, and then it's going to be a lot steeper faster. So when it is to the left of the y-axis, this curve is actually lower than the base E curve. But once you get past x equals 0, this curve is actually higher than the base E. So notice it comes under, crosses 0, 1, and then it actually is higher than the other curve. And again, you need to know which way things are going. Now, this is not a translated curve. So for this curve, the asymptote is still the same. The asymptote is still y equals 0. It has not been translated. All right, let's flip the page and we're going to do a little bit more practice. So Roman numeral 3, practice. All right, first one we're going to do, y equals e to the power of 3x plus 1. Okay, so first thing we're going to do is describe the transformations. Remember, you always start with the x's first. This value has been multiplied by 3. So we have a horizontal shrink by a factor of 1/3. And again, we're comparing, the base graph of this, of course, is y equals e to the x. The base graph for all of these is something with the same base, but no number multiplied by the x. So compared to this, horizontal shrink by a factor of 1/3, and then there's a +1 on the outside. So it's a vertical translation up 1. All right, so that is describing the transformations. Now, if you want to figure out how to graph this without a calculator, you can't just plunk in x values and multiply by 3 and calculate it out. That will take you forever. It's a lot faster if you go by steps. So let's start with y equals e to the x, our base graph. And we're going to use 0, 1, and -1. And again, these are almost good values to memorize. E to the 0 is 1, e to the 1 is 2.7, e to the -1 is 0.4. Okay, so then now we're going to do the first transformation. Y equals e to the 3x. So we're going to take our 3 points and we're going to multiply all the x's by 1/3 because it's been a horizontal shrink by a factor of 1/3. So 0 times 1/3 is 0. 1 times 1/3 is 1/3. -1 times 1/3 is -1/3. And of course the y's stay the same. 1, 2.7, and 0.4. Okay, the second transformation is a vertical translation up 1. There's a +1 on the outside. So the x's are going to stay the same, but the y's are all going to gain a 1. So just recopy the x's, 0, 1/3, -1/3, and add 1 to the y's. 1 plus 1 is 2. 2.7 plus 1 is 3.7. 0.4 plus 1 is 1.4. You can see how this is a much better way to do this if you don't have a calculator to get your values. While I'm thinking about it, if you do have a fractional value that's being raised to a -1 exponent, remember that the negative means that 3 goes down and 2 goes up. They're not negative, they just change position. So I wanted to throw that one in there as a bit of a bonus because you'll run into it. All right, now that we've got our points, let's draw the graph. So draw a pair of axes. And I already know because the 3 is positive that this curve is going to go upward like this. I know because it's been vertically translated up 1 that my new vertical asymptote is going to go up 1 along with the graph. So I'm going to start by drawing that asymptote and labeling it y equals 1. This will make the shape of the graph much easier to get. Now you can graph this point by point, or if you've already run the strips, you can actually do the final graph because you show where the calculation came from. 0, 2, 1/3, and 3.7. 1, 2, 3.7. And pretty much you got to label all your points on this because they're all fractions and decimals. -1/3 and 1.4. It's going to get infinitely close to the asymptote and curve upward. And it has been horizontally shrunk by a factor of 1/3, so that pushes the graph inward, and what would normally be a nice lazy curve is then shoved inward and made sharper. That's what horizontal shrinks do. They make it sharper. Horizontal stretches make it flatter. So again, you need to keep those in mind when you're graphing so your graph looks all right. Okay, last one I want to do with you. This is probably one of the more complicated ones you're going to be faced with, but it's not that bad if you pick it apart. So y equals -2 to the power of 1 minus x. Now I picked this one because the x is out of order to use your translation rules. Also, you have a negative in front of the 2, and I want to show you how to calculate with that. All right, so in this form, we can't use our transformation rules. The x has to come first. So I'm going to work with this a little bit. I'm going to switch the x and the 1. Our rules also don't work if the negative is only on the x, but not on the number. So you have to factor the negative out, and then that would be x minus 1. This is now a form we can work with. Now, for the sake of clarity when calculating, I'm going to remind you that when you have a negative in front of a number, if that number is not in parentheses, then it's a -1 times that number. And the -1 is actually separate from the 2 and from the exponent. It's just a number out front. Okay, so this is our good form to use for description. So let's do the description, starting with the x's. Shrinks and stretches come first, then reflection. So it does have a negative. So you're going to reflect across the y-axis. That's the negative. Now we do translation. It's a horizontal translation, and remember it's always backwards. Right plus 1. And then we also have a negative parked out front. That is a reflection across the x-axis. Reflection across the x-axis. All right, so what we're going to do is use our transformations to get ourselves a good set of points that we can use to graph the function. All right, let's start with the first one. We're going to start with your base function. So your base function is going to be y equals 2 to the power of x. That's your base function. So x and y make a t-chart. We're going to use the same three values, 0, 1, negative 1. So 2 to the 0 is 1, like all things. 2 to the power of 1 is 2. 2 to the power of negative 1 is 1/2. Remember, it's not negative, it's reciprocal. Okay, so first thing is we reflect across the x-axis. So that would be y equals 2 to the negative x. In terms of points, our x is being multiplied by a negative 1. So 0 times negative 1 is 0, 1 times negative 1 is negative 1, negative 1 times negative 1 is positive 1, and the y's are unchanged. Okay, so that was our first one. Now we're going to go to our next one. Horizontal translation, right 1. So now we're up to y equals 2 to the negative x minus 1. So in this case, we're going to add 1 to all the x's because it is a horizontal translation, right 1. So 0 plus 1 is 1, negative 1 plus 1 is 0, 1 plus 1 is 2. The y's are unchanged, 1, 2, 1/2. Okay, the last one is the reflection across the x-axis, which is the negative 1 out front. So when we reflect across the x-axis, all the y's change. So we're going to multiply all the y's by a negative 1. So we now have a negative 1, a negative 2, and a negative 1/2, and the x's are unchanged. And those are 3 really good points for graphing. Now I could go through the entire process of transformation, but I think you know what things should look like. But let's speculate just a little bit. My pen is dead. There we go. Let's speculate which way this thing should be going. So I've got a curve. The original one goes that way. And we reflect across the y-axis. Here's your y-axis. So here, it should now be going that way. Then we do a horizontal translation right. It should move to the right. And then reflect across the x-axis, it should be down. So it's going to be moved to the right and down when we're done with it. That's what the ultimate one should look like. So let's plot our last set of points and see if it agrees. 1, negative 1, 0, negative 2, and 2, and negative 1/2. Now the question is the asymptote in the same place or has it moved? Well, here's your horizontal asymptote. It only moves if you vertically translate up or down. This hasn't been vertically translated. So the asymptote actually is in the exact same spot as normal. Y equals 0. That hasn't changed. Your curve comes down and gets really flat looking without crossing. So yeah, this ended up going the direction we thought. So one more time, the original curve, the black, should be curving upward. Then we reflect across the y-axis. So it flipped, it's now going downward. Horizontal translation 1 to the right, it moved. That's why this is at negative 2 instead of negative 1. And then reflect across the x-axis, this is your x-axis, down it goes. So yes, that looks like it should. Okay, so last thing before we wrap this up, we're going to do domain, range, and end behavior. Okay, the domain of this, x's go infinitely left, infinitely right. So that's pretty easy, negative infinity to positive infinity. This will be the domain most of the time. Now for range, because exponential curves are bounded, you're going to have an exclusive boundary on all of them, at least somewhere. So our y values go from negative infinity up to but not touching the 0, so exclusive on the 0. If you want to get really fancy, you can say 0 from the negative side, but it just needs to be a 0. Okay, end behavior. So we're going to use limit notation. So the left side is always the same no matter what problem. The limit of f of x as x approaches positive infinity. The limit of f of x as x approaches negative infinity. So as we go infinitely to the right, the y values are getting close to 0 from the bottom. So 0 from the negative side. As we go to the left, the y values are going down, 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 down. So they're going to negative infinity. In general, your end behavior will always have one of these that expresses the asymptote. Go ahead and flip back to example 1. I just want to make sure that you're good on these things for these exponential curves. Let's look at example 1 again. So if you had to do the domain, the x values are infinitely left, infinitely right, so that's easy. Negative infinity to positive infinity. Now the range. This one starts just above 1, so the lower bound is a 1, exclusive, and it shoots up. It goes to positive infinity. So that's your range. Okay, end behavior. The limit of f of x as x approaches positive infinity. The limit of f of x as x approaches negative infinity. And I do want you to write that part. Even though maybe in the key they shortcut it, you don't get to shortcut. You need to memorize this so well you never forget it. So as x goes to positive infinity, the y's are shooting upwards. They're going to positive infinity. As x approaches negative infinity, the y values are approaching the asymptote, which is 1. And it's approaching it from the top side. So 1 from the positive side. Okay, I hope that was helpful. Have a good rest of your day.